Hi everyone. Maximize this. So no camera today because I left the camera at school. I'm doing this lecture from home. But today we're gonna have a pretty short little video on Thomson 6.3, which is a discussion. It keeps, spin and helicities are a lot of times used interchangeably. But let's discuss the helicity of these electron-positron annihilation. We learn how to calculate the cross-section for in 6.2. Okay, and we'll introduce this process, right, where let's look at the Feynman diagram again, right, where you have electron particle coming in and then a positron coming in, but right, since it's a antiparticle, we draw the momentum going into the vertex. However, since we're keeping track of the particleness with these little arrows, right, on the fermion lines, okay, it's actually antiparticle, so the particleness actually goes out of the vertex, so that way you can just kind of draw it this way, okay? And when you make the Feynman diagram, you start off here, and then you go backward, you march along, get to the vertex, march along, you get to the other electron, right? So that's how we utilize the Feynman rules in order to just write down what the matrix element is for this matrix. Then you put in the propagator and you write down the matrix element for this vertex, and then you can actually calculate I negative IM, and then when you square that, then you get something that's going to be proportional to your cross section. Okay. But right, so the whole point is that, right, we have momentum coming in, right? The photon existing between these two, we usually don't draw the line, any arrows in it, because, photons are not, it's really hard to determine like when things happen, in this intermediate state. So we don't even try to attempt to draw a direction to it because you actually don't know. But then you have momentum coming out. Okay, once again, right, you have a actual muon that's coming out, so that you have this outgoing particle line, and you have an actual anti-muon coming out this way. But since it's an anti-particle, you draw a particle line coming into the vertex like that. Okay. What was really neat is that so the electron, right, can be right-handed or left-handed helicity. The anti-electron can be left-handed, right-handed, right? So are the muons, right? You have the same thing here. So in essence, you actually have 16 different combinations of handedness coming in and out in general. But when we went to the relativistic regime, where basically, the energy of the particle is much bigger than the mass, even the mass of the muon, right? And therefore, right, we can write down this equation where it simplifies, where momentum and energies are basically equal to each other at this point, right? Because of the p squared plus m squared equals e squared, right? If these are the big guys, right, this goes to zero, right? So the magnitude of the momentum basically is the energy. Okay. And using this, we actually were able to calculate, right, using these spinners multiplied by a bunch of gamma matrices, right? There's actually a gamma 0 here also, right? Because it's inside this adjoint. And then the antiparticle spinner, right? And what happened is that when you do this, okay, you end up with two helicity combination that is non-zero. You have two that are zero, okay, right? Namely the right and the left, okay? And this is sort of an interesting thing, and you have the same thing for the electron, right? That what you do is basically just replace the momentum with the electron momentum, and then you'll get something very similar where you have cosine of 0 and then sine of 0. But I won't write that again. But right, you have once again, right, the same thing for electron, right, where J E R R equal to 0, J E L L equal to 0 also, right? And that's the important point here. It's like somehow these currents are 0, and we wonder why, right? Is it just luck that that we don't have to compute 16 different combinations of these things, because each of these, right, you have to multiply them from with the electron version of it, and you have all these combinations. But since you have just 2 non-zero, right, 2 out of the 4 non-zero, right, and then you have 2 out of the 4 that's non-zero, 2 times 2 gives you 4 instead, so we just have to calculate 4 of these, okay? And the little homework problem in 6.2 really force you to just see all these calculations, right? Okay, but interestingly, right, it's actually not an accident that these right and left currents are 0. Okay, so remember diagrammatically, hopefully I spelled that right. I probably didn't spell that correctly. Okay, the diagram from 6.6, right, figure 6.6 here, right? What you want to do, right, when you draw this version of the diagram, right, where it's kind of a spatial diagram instead, right, what you can add into it, right, is the helicity vector, right? When the helicity vector is going to in the direction of the momentum, right, this is considered right-handed, right? When the helicity vector is going opposite direction of the momentum, right, this is considered left-handed, right? So this initial state, right, is RL. So these are the electrons, right? E minus E plus, right? Similarly here, right, you have the momentum vector aligned with the muon, right? So this will be the right-handed. Oops. I think I'm going to draw this again in a little easier way to understand it. And then you have the antiparticle that's coming out, but then your momentum vector, your helicity direction is opposite of the momentum, so therefore it's left-handed. Okay, I won't go through the same thing with all these, but these are the 4 combinations that are not 0, right? Right. So the book tried to give you a really good discussion or a good example of how you can actually, right, instead of having the z direction along the electron, you can actually redraw these diagrams where it's actually the muon that comes out along the z-axis, because you can just kind of rotate this axis, right? Let me try to draw it. Okay, let's see. Let's say we have the muon coming out, mu plus coming out here. Let's draw this one, right, where it's LR to LR. Okay, so in this case, right, the muon helicity is aligned with the momentum, so this is actually a right-handed anti-muon. Okay, and then you have the mu minus, and since this is right-handed, this will have to be left-handed. Okay, and it's actually the electron. Let's say we have the electron coming in this way, and then the electron coming out, right? Okay. So this is no momentum going out. This is momentum coming in. Okay. And since we want a left-handed electron, we want the momentum vector to be opposite of the the helicity vector to be opposite of the momentum, and we want a right-handed anti-electron, so we draw it along this line. Okay, right. So it's sort of an interesting diagram, right? It seems like, right, if we look at this kind of position-wise only, right, we have some sort of helicity going into the interaction, and then the same helicity coming out. Okay, so that may be one way to think about that. So same thing with the electron, you have some sort of helicity going into the interaction, the same helicity coming out. Okay, and this is actually more important. Okay, this is, I think he's trying to showcase why even transforming the to a different axis, you still get the same Lorentz invariant matrix element, and I think you should read through that. But what's even easier to understand, at least to me, is that since these are Lorentz invariant matrix element, you can transform your axis however you want, you will still get the same answers, just from the fact that we calculate this using Lorentz invariance. Okay, and that's what's, what the whole chapter 2 through 3 was, all that pain of us going through all of those special relativity and doing a Lorentz invariance version of quantum mechanics. All that pain was just so that we can always calculate this and don't worry about how we rotate the axis, which way we're boosting things. There is a simplification here just because in these high energy regime, right? It's going back up here, right? This is a frame dependent thing, okay? But, right, as long as your electron and positrons are at high enough energy, it actually doesn't matter which frame reference you're in, okay? But what's more profound in this section, and I think Thompson is trying to highlight this, is that the helicity state in any quantum electrodynamic processing in this relativistic regime where you have energy much higher than the mass, helicity is actually conserved, okay? And that's what these kind of arrows coming in, coming out are trying to show you guys, okay? So let's examine this instead of drawing the physical position of the incoming and outgoing particle, let's examine this even using Feynman diagrams. We can even do that, okay? So let's draw this one, right? Right, left, and let's not draw that. Let's draw this one, okay? Right, left, and then left, right. Okay, we're gonna do this one. 2, left, right. Okay. So let's draw the Feynman diagram version of it. So it's a electron, right? Positron annihilating. Okay, and I'm gonna draw the particle line, right? Okay, and then we have a photon. Okay, and it spits out a muon, anti-muon, right? And these are the direction of the particle line. What I'm going to add on top of this, right? I'm going to add the momentum directions, right? So this is called P1. We draw this in this direction. This is P2. Draw this in this direction, right? They're both coming into the vertex. P3 is leaving the vertex, right? P4 is leaving the vertex, right? And then next, I'm going to draw these little helicity direction on top of it too. Okay, so this arrow is tracking particleness, this arrow is tracking momentum, and then we're going to draw one more to track the helicity of it. Okay, so I'm going to draw it like this. Hopefully, it matches what the book is doing, right? So this is, since this electron is right-handed, the momentum and the helicities are in the same direction as each other. Since this is left-handed, it has to go out this way. Okay. And then particle 3, right, is left-handed, right? So left-handed, I want it to not align with each other. Okay, oops, let's do that, right? And then we have right-handed, so the momentum and the helicities are actually aligned with each other. Okay, so this is like the Feynman diagram version of this with a little bit of add-on, right? Usually you don't put the momentum and you don't put the helicities, but this would be hopefully useful for us to understand a little bit, okay? Okay, so the electrons, right, and the muons are all spin 1/2 particles, right? That's why they're Dirac particles, right? So meaning, right, a right-handed, right, electron, right, will have a spin of 1/2, right? And then since we normalize it with the momentum, the helicity, right, the helicity of an electron, a right-handed electron, now there's so many subscripts, okay? It's actually have a value of positive 1/2, okay? A left-handed positron, the helicity of that left-handed electron, okay, since, okay, right, it's left-handed, you would think, oh, it should have a value of negative 1/2, right? But remember, when we did this particle to antiparticle, right, we basically changed the helicity operator to negative of the helicity operator, okay? We did a little sign flip there, okay? So what's actually happening is that the positron, okay, the helicity of the positron, right, is actually negative 1/2, right, due to this sign flip of particle to antiparticle, u to v, right, okay, and therefore is actually plus 1/2, okay. So let's redraw this little vertex on the left-hand side here, right? So basically, right, if I'm just not thinking about direction, but actually just like the magnitude of things, right? We have an electron coming in, a positron coming out. Well, a positron coming out, but it's really coming in because it's a antiparticle. Okay, so we have something with the spin helicity magnitude of 1/2 coming in. You have a spin a magnitude of 1/2 coming in. Right, I'm not even trying to draw the direction here. Okay, this combines, right, to a spin of 1. Okay, the spin at the vertex, right, equals to 1. Okay, so what happens is that, well, whatever comes out here has to also have a spin of 1 also. And luckily, photons have either spin plus or minus 1. Okay, remember, since the photon is massless, the spin 0 state is actually not possible. So therefore, right, you can actually have if so I know I'm also switching between spin and helicity a lot, but right, so when you're drawing Feynman diagram, what's really important is that, okay, do I have a spin 1/2 particle come in, I have a spin 1/2 particle coming in, right? If those spins, right, those spins has to come in, at least for quantum electrodynamic, those spin has to come in to be the same magnitude, right, in order for it to produce a spin 1 coming out, okay? And let's finish up this diagram. I'm going to extend this out a little bit, okay? Right, since you have a spin 1 here, right, this is conserved, right? Whatever comes out of these two lines also have to have a spin of 1/2, okay, in magnitude, okay? And therefore, right, you have to have a, let's say we're doing muons and mu plus and mu minus, right? So whatever comes out here, right, if its momentum is going this way, right, so we're doing, which one are we doing? Left, right? Okay, so this has to be left-handed. So therefore, right, let me just do the same color coding as we did above. Okay, you have the momentum coming out, okay, and then you have the spin in the opposite direction, but, right, so this is actually a spin of negative 1/2, okay, and then, so the helicity of the left-handed muon, right, since it's a particle, we don't do the sign flip, right, it's actually negative 1/2, okay. Let's figure out the helicity of this, right? So it has to come out right-handed. So therefore, the helicity and the momentum actually are aligned with each other, okay? Right, but since this is a right-handed anti-muon, right, we have put this little extra negative sign here because you're going from a particle to a anti-particle, right? And then this magnitude is 1/2, so that's why this right-handed thing here, right? So therefore, right, this actually comes out with a net spin of negative 1/2. Negative 1. Okay, right. Since you came in with a spin of 1, right, but then the photon can actually change to the spin along the z direction to negative 1/2. So this is okay, right? Right, where you're coming in, but the main thing that you want to make sure is that the helicity of these incoming particles both add up to 1, and then whatever either plus or minus 1, okay? And the helicity of the outgoing particle, right, there's actually a negative here now that we figured out, also comes out to be either plus or minus 1/2, because the photon in between of them can only have a helicity state of either plus or minus 1/2, okay? Also known as the two polarization state. They're not exactly the same thing, but you can just think about the photon as having to have this conservation of helicity also, okay? So hopefully that'll help you make sure that you're drawing the right Feynman diagram and how they're matching up with each other.